This is MGF 1107, Chapter 13, Section 1. This deals with what we call graphs, paths, and circuits. All right, just on page 802, which is the start of the chapter, it says, suppose that you are a Girl Scout leader and you must deliver cookies to 15 different homes. You will use your car to drive from home to home to deliver the cookies. You realize that you have many possible routes to accomplish this task, but how can you determine the shortest route? This is what this chapter is all about. This chapter is all about using math to be able to have the best route. There's a lot of problems called touring, like especially in the state of Florida, where we have so many vacation sites. And people have to plan vacations. They have to limited amount of time, limited amount of funds, so they have to use mathematics to plan and get the most out of their money and their time. Okay. Here's an old problem that was presented a long time ago. It says the study of graph theory can be traced back to the 18th century when people of the East Persian town of Konsberg sought the solution to a popular problem. Coensberg was situated on both banks of two islands of the Prigal River. From figure 13.1, we see the sections of the town were connected with a series of 7 bridges. So here it is here. Okay? It says the townspeople wondered if one could walk through town and cross all 7 bridges without crossing any of the bridges twice. This question was presented to a Swiss mathematician, Leonhard Euler. Euler's very popular, or Euler. To study this problem, Euler reduced the problem to one that could be represented with a series of dots and lines. So what he did was he used graphing theory in order to solve it. And you can see this over here on page 308. So what he did was use vertices to mark the points of the land. So here's point B, which is right there. Here's point A, which is that side of the land. There's point D here. And then point C is right there. And then what he did was use a series of lines to draw the bridges. So that when we start this chapter, we've got to understand a few definitions. All right. So when we go to represent any kind of map or any kind of diagram with a graph, then a graph is a finite set of points called is a finite set of points called vertices, connected by lines segments called edges. All right. So this is what this is doing here. These are the vertices, the A, B, C, D. The lines are called the edges. And some other definitions. An edge that connects a vertex to itself is called a loop. So here I've drawn a loop here. So see, whether we go this direction or go this direction, we come around and we come back to the same vertices. This is called a loop. We would represent this loop as B to B. Okay. We also have in this diagram vertices. I've labeled them or drawn them with red dots. Notice that they are all capital letters. And then anytime we draw a line from one vertices to another vertices, that's an edge. And the direction we're going is how we label it. So for instance, if I draw my line from A to B, or A to D, then I label it AD. But if I draw my line from D to A, I label it DA. That gives direction to my line. Here is one more example problem I want to go over. It says the Navy Region Southwest, NRS, is a division of the United States Navy. NRS includes all Navy facilities in the states shown in figure 13.5 on page 804. Construct a graph to show the states that share a common border. States whose border touch only a single corner point will not be considered to share a common border. So we'll go over to 804. Here's the diagram here, or the map. You can see we have California, Nevada, Utah, Colorado, Arizona, Mexico. So what it's asking us to do is to basically, wherever it touches a common border. So, for instance, if we look at this, here's the diagram we get. Okay? So when we look at Nevada, Nevada touches California here. When we look at California, California touches Arizona here. If we look here, Nevada touches Arizona here. That's the reason we have that diagonal line. Up here we have Utah touching Nevada, which is what we have here. Okay. And then coming down here we have Utah touching Arizona. And then we have Utah touching Colorado, which is right here. And then right here we have Arizona touching New Mexico. So see, this is what they did, was they wanted to place vertices where there was a connection with the states themselves. Like for instance, if we look here, see California, Nevada, and Arizona all touch here. So see how this is aligned with Nevada, this is aligned with California, this is aligned even with Utah coming in here. Okay? Some other definitions you have to be concerned with in this particular section is we have a path, the definition of a path. A path is a sequence of adjacent vertices and the edges connecting them. So really a path is nothing more than a line or an edge. Okay? A circuit is a path that begins and ends at the same vertex. All right? So if we start at point A, when we finish our path, we're going to end at A. That's what a circuit is. A bridge is an edge that, if removed from a connected graph, totally connected graph, the graph would be disconnected. All right? I'm going to go over some example problems on that. Okay? All right. So looking at this, here is what we would consider a path. Okay? Here's a diagram. Here's our graph of something that we've, I think they've just made this up. But basically what would happen here is if we wanted a path from C to B, we might want to go and have to go through D and A, so we want to go through all those points. We would go C to D, D to A to B. We could also go, here's another path, we could go C to A to D, D to B. So understand in these problems right here, there are multiple answers and multiple pathways that you can take. So our next definition classifies graphs themselves. A graph is connected if for any two vertices in the graph there is a path that connects them. All the graphs we have studied thus far have been connected because a path existed between each pair of vertices in each graph. If a graph is not connected, it is considered to be disconnected. So if we look at these examples here, we can see that letter A is a disconnected graph. So is letter B. Letter C, however, is a connected graph. Or I'm sorry, it is not connected because we don't have a connection between A and C. We don't have a connection between C and D, so on and so forth. So we come down here, if we now connect, here's this same diagram here. If we now connect A to B, we have a bridge and the graph is considered to be connected. If we come over here, we could either draw a line from C to E or D to F. Either way, this is considered to be a bridge and we still have connection because this side is connected to this side. We come here, and here's the one here, we draw a line from A to B and it's considered connected. Remember, we could draw a line A to C, C to D, or D to B. It would still be connected. That means every point is connected to every other point. In other words, coming from here, we can go from point A to point B. We can go from point C to point A. That's what we talk about being connected. There is a path that allows us to go from one point to another point.